millions of little constraints and the features that God built in to capitalize on chaos. Here are all these oxygen molecules, for instance, all these water molecules just moving around at random with no particular purpose of their own that are serving the designed purpose and intent of their creator, the one who created them, and the one who created the system to capitalize on this chaos. And a lot of things depend on that. The nerve impulses, the nerve ending gets to a muscle or a gland, there's a little gap at the end. And so what happens? The nerve impulse is kind of a chemoelectric signal that goes around the nerve membrane. But here's the end of the nerve membrane, here's the beginning of the muscle or gland, and so there's this little gap in there, like the synapse between one nerve and another, or the myoneural junction between a muscle and a nerve. And so how are you going to get across that? Well, the answer is to dump a signal like acetylcholine is a common one. There's several of these chemicals that carry the impulse from a nerve ending to another nerve ending or a muscle or a gland. Well, how do they get across? Well, they diffuse across. And so the gap, again, has to be the right distance. If it's too wide, the signal will never get there, etc. So you have to have the distances just right. And in this particular case, like in nerve impulses, the amounts have to be right. And so in this little gap, there's all say the chemical that's being dumped in, the nerve signal transmitter, neurotransmitter, might be acetylcholine. Well, in that junction, there's a chemical, cholinesterase, an enzyme, whose job it is to break down acetylcholine, to destroy the neurotransmitter. And you might think, why would God put in a destructive enzyme like that? And the answer is so that when you bend your arm, you can quit. Otherwise, you bend your arm, just go like that. You need a stop signal. So you need go and you need stop. And so this stuff is dumped into the nerve gap, and it diffuses across. Now that's where almost all the reaction time is. When we're in driver ed, how long between the time you see danger, and you get your foot off the gas pedal and onto the brake. A lot of that delay is that diffusion delay, getting those neurons. It goes pretty fast down the nerve itself, but then that's where a lot of the delay is built in. And the amount's crucial. If you're only thinking about strangling your little sister for messing up whatever you just made, there may not be enough of a signal dumped in there. The breakdown enzyme, the cholinesterase, breaks it all down, and the signal doesn't really cross. Or if you're really, committed to this action, you may dump a whole bunch of this in, and the impulse, continues for a longer time. And then there are competing impulses. You could also have a strangler, no, don't strangler, chemical stimulators and inhibitors all fighting it out, in terms of diffusion, going across this little specially structured, sealed, controlled little gap. And so diffusion itself plays an enormous number of roles in living things, thanks to what? The design of the system capitalizing on the random motion of the molecules involved. It's not the random motion. Now, the random motion couldn't do this. If the membrane distances and the receptors and the stop signals and all that weren't part of the system, diffusion doesn't get the credit. It's the designer who created a system that can harness this kind of otherwise chaotic motion that deserves the credit here. All right, well that's diffusion. Can you see diffusion? And the answer is yes. In several different ways you can detect it. One, by the sense of smell. If I had a bottle of perfume up here, it should have, took off the top, the first row would begin to pick up the aroma and gradually would spread out over the room. So you can detect diffusion in ways like that. You can also see a kind of diffusion under the microscope. Brownian motion, and sometimes you don't need a microscope. Now this has probably never happened to any of you, but you've probably heard about friends that were sitting in church and not paying as much attention as they ought. And here's a sunbeam coming into the window, and no matter how often the custodian goes over, there's always a little dust in the air. And so you look at the sunbeam going through here, and you see little dust particles in the air. It's possible to get totally captivated by these. You don't want to, or at least it shouldn't be in church. But you can see these things. Now there's kind of a drift That's just air currents. You know, they might be flowing. But if you pick one particular little particle of dust and watch it, you know, it'll be bouncing around, up, down, backwards, forwards, left, right, toward you, away from you, just this random little dance. Named after Bill Browning, it's called Brownian motion. You've all seen Bill dance around, right? But at any rate, this is a phenomenal thing, and I just love watching this under the microscope. Proteins are way too big to move under their own power. If you just look at proteins under the microscope, you know, they're just sit there. They can't do anything. You put them in a solution of water, you don't see the water. But the impact of the water molecules on proteins or clumps of proteins or small dye particles or ground up leaves and so on is such that you see this vibratory motion. And it just goes on and on and on and on and on. You know, room temperature just goes on forever until the particles break down so you can't see them anymore. And of course, you can take these things. I used to have students make a little hanging drop suspension, and you can put it on a hot plate for a few minutes, or a little bit, and then take it off. And now all these particles are dancing ever so much faster. And then you stick it in the freezer for a few minutes, you know, and then stick it in there all, you know, now they're all slowed down. And so even though you don't see the random motion of the water molecules, you see their effect bouncing into larger particles, just like the dust particles are not moving under their own power. They're being whapped by air molecules from the left, right, top, bottom, forward, backward, and being slapped around like that all the time. Well, Brownian motion is one of the most awesome forces in the universe. And it does two things. It makes life possible, and it kills you. Okay, so you can't live with it, you can't live without it. And so if you had no Brownian motion, in other words, you just freeze the cell so the water molecules weren't moving, there's no life. You can take the water out of it, freeze dry it. And if you take the water out of a living cell, you take the life out of a living cell. You put it in suspended animation. The particles just sit there not interacting anymore. You add the water back, it's almost like adding life back. Now, you know, some evolutionists get carried away by this and think, oh boy, if there's a planet out there, a moon of Jupiter that has a drop of water on it, maybe there's life there. Now, water's necessary, but not sufficient. And so just finding water doesn't mean there's anything more there than water. But in order to find life there, as we understand,